I think we can start. So it is my pleasure to introduce Daniele Astolfi, who is visiting us these days here in Politecnico di Torino, and he's a researcher at LAGEPP CNRS in Lyon. Daniele Astolfi received a joint PhD in control theory from University of Bologna, Italy, and Mainz Paris Tech in France. He also received the 2016 Best Italian PhD Thesis Award from SIDRA, and his research focuses mainly on nonlinear system theory with application in observer and regulation. And today, Daniele is giving us a talk on new result in synchronization of nonlinear multi-agent system, which is also promoted by the IEEE-CSS Italy chapter. So please, Daniele.
Thank you a lot, Diego, for the nice introduction. So today, as Diego introduced, I'm going to talk about new results for synchronization, and more specifically on the consensus problem, in which the agents are described by nonlinear system, and I will try to be as much as general as possible on this nonlinear dynamics. First of all, I want to thank my collaborators. So my former PhD students, Mattia Giaccagli and Samuele Zoboli, who are now assistant professor and CNRS researcher in Nancy and Toulouse, respectively. My PhD students, Alexandre Cellier, and my collaborators, Giacomo Casadei from Gypsa Lab in Grenoble, Vincent Andrieu from my lab, and Luca Zaccarian from Toulouse and Trento, who was the double petition. So, okay, without further ado, this is the plan, the content of my talk. So first of all, I will briefly make an introduction about what is the synchronization problem that I'm going to discuss today with you. I'm going to then make some highlights about contraction theory, which is the main tool that we will use to solve our synchronization problem. We will address the continuous time case, basically when the agents are described by continuous time dynamics. Then briefly discuss the discrete time case, and then go towards some conclusions and perspective. So multi-agent system and network theory have been very popular, well, in recent years, I would say since the last 20 years. It has been a very hot topic, because there are many applications in which we can use this framework, such as robotics form, electrical power networks, and so forth and so on. So I will not talk about application today, but you all know that we can use it, this very general framework. One thing about consensus and synchronization, which are typical features in these multi-agent problems, with consensus or synchronization, we mean that we want all the agents in the network to have the same behavior and exchange information so that to achieve this goal, this common goal in a distributed form, is that we can classify this synchronization problem with many aspects and types. And so there is a huge literature about it, and this is why also I will not mention too many other papers, because the literature is so big that then it's hard to know who has done who. These are the main features. So usually the information is partially available, meaning that the agents in the network may communicate with the neighbors, but it cannot have a global information about what's going on in the overall network. We would like to have algorithms which are distributed and decentralized. The communication office is limited, okay? And of course, the complexity may increase with the numbers of agents in the network. And so this is why we can characterize these problems from many points of view, but in particular from the point of view of graph theory. You can think about graph, communication graph, in which the communication is directed or undirected, meaning that I can talk with a neighbor, but the neighbor cannot retrieve information from me. This is the case of directed case. Or in the case of undirected communication, if we share a link, if we share information, this is bidirectional. We can have weighted or unweighted graph, meaning that the information that is going through the agents can be weighted or not. We can have fixed time varying switching topologies graph, agents that add to the networks. Lately, there have been topics like open multi-agents. So it's very large, the overview. And of course, we can also talk about multi-agent system, looking at what is the dynamics of the single agent. So we have a linear, nonlinear dynamics, homogeneous or heterogeneous agents, meaning that all the agents in the network have the same kind of dynamics and same parameter. In this case, we talk about homogeneous agents, or heterogeneous. Maybe we want to synchronize the behavior of a robot which is walking with a drone flying. In this case, the dynamics are completely different. And in this case, we talk about heterogeneous agents. We can have the case in which the communication between agents is just the full state or just an output. We can have continuous time, discrete time. So the panorama is, the overview is very large. So today I'm trying to focus on some classes of problems. In particular, we will see, I will consider both directed and undirected graph. To be specific, in the continuous time case, I will talk just about undirected graph. In the discrete time, we will talk about a directed graph. We will see later on why there is differences. With weighted graph, fixed topologies. So we will not talk about topologies that can switch over the time. The main focus is really what's going on when the agent's dynamics is nonlinear. How can we design the distributed decentralized feedback law? This is the main challenge. The agents will be homogeneous, and we will consider to simplify the case in which all the full state of the agents is available to the neighbors. Okay. The synchronization problem, if we want to fix it from the mathematical point of view, we have a certain number of agents in the network that have general nonlinear dynamics. And we want to find some feedback control U that depends only on the own states and the states to which the agent is communicating with. And we have two goals, I would say. So first of all, we want to achieve a common behavior so that all the agents asymptotically have the same behavior. And moreover, we have the constraint that when the agents have the same behavior, we don't want to use the network to communicate information. So the control input U has to go to 0 when all the agents are doing the same behavior, because otherwise we will just use information not to. Okay. And so in general, of course, one may think I just stabilize all the agents to an equilibrium. But in this case, most likely this objective, that the input U is 0 when all the agents has the same behavior, in general, this is not achieved. So stabilizing everything to an equilibrium is not what we want. So we really want the input U to switch off, to vanishes when they have doing the same behavior. And so we want to really to preserve the natural behavior of the plants. So this is a very short highlights on the Laplacian matrix, which is one of the main objects that we will use in our presentation. Although the focus is not really on the aspects concerned to it, but just to recall, when we want to describe a graph, we have 3 elements. We have the vertices or the agents, the number of agents that we have in the graph. We have the edges, which are the link connecting the agents which can communicate and share information among them. And we have some edge symmetries which describe the weighting of the flow of information. So with all these objects, we can construct the Laplacian matrix, which is the main object that we can use to describe the graph. And actually is the only one that the main that I will use in this presentation. And this is just a nice property of the Laplacian matrix is that, so if the graph has a directed spanning tree, meaning that, for instance, if we have a case in which the graph is directed, meaning that the communication is not bidirectional, if there is, for instance, a leader, the leader must share his information with some spanning tree to everyone. So the information must go to arrive to everyone. Well, in this case, the Laplacian matrix has a very nice property, which is the fact that its eigenvalues will the eigenvalues of the Laplacian matrix. So the first one is 0. So there is one eigenvalue which is 0 and it's simple, and all the other eigenvalues have positive real part. And this is also the case of undirected graph. In this case, in the case of undirected graph, so if the communication is bidirectional, We also typically talk about a connected graph, because basically we can connect everyone through some path. And again, in this case, the eigenvalues, one is 0 and the other are positive real part. Okay, so what synchronization mean? Well, we can define this object from the mathematical point of view as a stabilization problem to a manifold. In particular, if we describe this manifold in which all the states are equal, the synchronization problem means that we would like the distance to this set to go to 0 exponentially. So in this case, we will talk about exponential convergence. And if the distance to this set goes to 0, well, we have achieved our synchronization problem. And we can talk about, of course, local synchronization or global synchronization, depending on the attractivity properties of this set. In this presentation, I will try to solve this synchronization problem in the global context. So meaning that we would like this property to hold for any initial condition of the objects. And again, our synchronization problem can be formulated as finding a set of control feedback phi, such that if they are not communicating, well, the derivative with respect to the state is 0. And this manifold is locally or globally uniformly exponentially stable for the closed loop dynamics. So this is mathematically stated the problem. Well, this is a very short review. There exist many results in literature. For linear system, nonlinear system, there are some solutions. My focus today is to design this, to achieve the synchronization goal for this general input-affine nonlinear dynamics, for which, to the best of my knowledge, there was no solution so far. And to do this, we will rely on contraction properties I will show very soon. Now, before going towards the nonlinear case, it is instrumental to recall very briefly the linear case to understand what is behind the synchronization problem, what is the core of this solution. So for continuous time system, we have a very nice property, which is the fact that if you have a system described by a linear dynamics, if the pair AB is stabilizable and if you have some connectivity property of the graph, then you can always achieve synchronization. This is a very strong property. And the way we do it is to find just one feedback k. And this is why it is somehow decentralized and distributed, because the k is unique and all the agents will use the same k. So you will not redesign the k according to your position in the network. This is a very crucial point of the synchronization problem. And the key point is how to find this feedback gain k. The way it's done is through the algebraic Riccati equation. And typically what we do is to use this algebraic Riccati equation and find the k according to the standard LQL problem, actually. And the interesting point is that if you do a proper change of coordinates, the synchronization problem can be seen as a simultaneous stabilizability properties of many systems of this form, in which, however, the lambda I, which are the eigenvalues of the Laplacian matrix, appear modifying the control gain. And if you want to find a solution to this simultaneous stabilizability property, well, one way is to use, indeed, the solution of the algebraic Riccati equation. Indeed, this matrix can be stabilized in the presence of the lambda I by just augmenting the parameter k. And so at the end of the story, your design is very simple, because what you do is to find the k according to the algebraic Riccati equation, and then select again kappa, which is large enough. So how large? Well, you take kappa larger, typically, it depends on the connectivity of the graph, so typically on the real part of the smallest non-zero eigenvalue of the Laplacian matrices. And this is a very nice property due to the fact that we have what we call infinite gain margin property. Now, the infinite gain margin property is the fact that if k stabilizes the pair AB, then A minus kappa bk is Hurwitz for any kappa larger than some value. This is the really infinite gain margin property. And this is what behind this the solution of the synchronization problem. And so the question is, can we extend the same paradigm to the nonlinear framework? Meaning that we would like to find a feedback gain in the nonlinear context with the same property, so that we have a feedback that depends on the single agent dynamics and possibly just one tuning parameter that depends on the connectivity of the graph. And to do this, we will rely on contraction theory. So why contraction theory or incremental exponential stability, which are often actually it's the same wording for the same property that we are looking for, it is useful. So let's consider an autonomous dynamics for simplicity. X dot is equal of f of x. And we denote with capital X the solution at time t starting from initial condition x1, for instance. So we pick two different initial conditions and we let the flow and we consider the trajectories of this dynamical system. And we say that the system is contractive or incrementally globally exponentially stable. So the delta is for incremental. If the distance between the two solutions converge exponentially to 0. And uniformly, also this is important because the K's and lambda are the same. So we have a uniform global exponential property. Of course, this property is also equivalent if we duplicate our system. So if we suppose to have x1 dot is equal to f of x1 and x2 dot is equal to fx2, and we look for the synchronization manifold that we discussed before, this incremental global exponential stability property is also equivalent to a uniform exponential stability properties of this synchronization manifold. And this is why this contraction property is actually the property that we want to enforce in our synchronization multi-agent property, which is behind it. Of course, for linear system, stability is equal to incremental stability, and this is why it's somehow magic that everything works so simply.
So contraction would be k equal to 1? Or
yeah, often you can define contraction with equal to k equal to 1 if you find the right metric for which, or the right distance for which you are contracting with k equal to 1. In this case, it's just some overshoot that we take into consideration. So that's why I talk about contraction, but actually here I'm precise with incremental globally exponential. So the setting that I'm going to use to build somehow some feedback that can enforce contraction to a dynamical system is the one based with the metric approach. So a sufficient condition to have incremental globally exponentially stable is the existence of, so we look for a matrix function P, which define a metric somehow. This P that depends on the state X is uniformly bounded, okay, for all X. And we have that its derivative, its Lie derivative along the vector field F. So here there is we have to be a little precise about what this object is. I will give the example later to simplify it. So basically the Lie derivative is uniformly negative. So what is this object? So this is P times the Jacobian of F, but since P depends on X, you have also to make the derivative with respect to of P with respect to X. And so this is why there is this extra term here. So if you have, for instance, a linear time varying system, you could imagine to this as it were the Lyapunov equation in the time varying case in which you have also P dot plus PA plus A transpose P. So basically this is in the interpretation. So this is a sufficient condition. The existence of a metric satisfying this condition is a sufficient condition for the system to be incrementally globally exponentially stable. And actually, this condition, the existence of such a metric, is also a necessary condition under somehow some smooth regularity. So if F is C2 and it is globally Lipschitz, then this condition becomes also necessary, not only sufficient. This is a good starting point to make our analysis. So there are many references in the literature here. I just cited some of the authors that contributed to this, in particular the necessity, which is a little less known in the literature, has been done by Andrew Eprali in 2017, I think. Okay, so this condition basically is a somewhat generalization of the Lyapunov matrix inequality. So basically, if you have a linear system, then P is constant, the Jacobian of the vector field coincide with A, so you actually boils down to the Lyapunov matrix inequality. So it's just a generalization in the nonlinear context. And what's going on is that P can use it to define a Riemannian metric and construct a Lyapunov function that will give you this delta, so incremental globally exponential stability. The way it is done, it's a little complicated, so I will not enter in the details. It's not the purpose of this presentation, but just to give an hint, if you want to do the analysis properly, you should take a path between two points, and then minimize along all the possible paths according to this metric, and then this will give you the construction of a Lyapunov function that will satisfy this property. So the Lyapunov function is it satisfies the standard sandwich bounds between 2 points, and it is exponential decreasing. So this can give you the property of global exponential stability, incremental global exponential stability that we were talking about before. Again, when the metric is constant, of course, the condition is just sufficient, not anymore necessary. It is also known in the literature as the Demidovich condition. This condition were found in the 60s in the Russian literature, so it's very old and it's very well known. In this case, the analysis it's much more simpler because if we suppose that we have these two conditions, and if we want to show the global exponential stability property, in this case, it's just about using the fundamental theorem of calculus in a proper way, because if you introduce the Lyapunov function, the quadratic Lyapunov function, which is just the distance between two dynamics, so the error between x2 and minus x1, and if you do the derivation, so you will use the fundamental theorem of calculus to recover the Jacobian, and then you will just use this property to have exponential stability. So it's very simple in this case. In the case of Riemannian metric, it's a little more complicated, tricky, but it can be done. Okay, so once we have this, we would like, I recall the overall objective is to make feedback design to solve our synchronization problem. So we consider now an input-affine dynamics, this form, so f of x plus g of xu. And we ask ourselves, can we find a control feedback such that the closed loop dynamics is incrementally globally exponentially stable? The answer is yes, through this sufficient condition. In this case, we don't have necessity, as far as I know. So we look again for a Riemannian metric P, satisfying this condition. So LFP is the object that we have before, and we have something that depends on the G. In the next slide, I will show that this is just the generalization actually of the algebraic Riccati equation, but in a nonlinear setting. And up to this, we need two extra conditions, unfortunately. We'll discuss about it in the next slide, what are these conditions. But if you have these three conditions satisfied, then alpha, that satisfies this integrability condition, is a feedback, is a proper feedback, which has the two properties we are looking for, meaning that the closed loop system is incrementally globally exponentially stable, and moreover, we have the infinite gain margin property. So this set of sufficient conditions, which of course is, we will discuss about implementation later on, because it's very ugly, it's a nonlinear partial differential equation, so it's not so easy to handle, and especially to find an analytic solution to it. But if you find a solution to this, then you will have a stabilizing feedback with infinite gain margin properties and contraction property, incremental stability.
Sorry, what is LG? And then
LGP. So this is the Lie derivative of the vector field G along P. So again, we have the three components. And just for some of you that may know, this condition is also known as control contraction metrics in some works by Zlotin and Manchester. So some remarks. So this condition, again, if you specialize to linear system, to linear dynamics, is nothing but the algebraic Riccati equation. Of course, here we use inequalities to make it simpler and not equality. So this condition, LGP, which again are the three terms, is known in literature as a Killing vector, because we need LGP equal to 0. So Killing was a mathematician, not because it's better. And of course, a trivial case of this condition is that when P and G are constant, this is of course satisfied because we take Jacobians of constant matrices, so everything is 0. So again, in the linear case, these three conditions are trivially satisfied by definition. And the third condition, it is an integrability condition. Why? Because we are working somehow on the variational system, on the differential system. So we design the feedback in the differential context, and then we need to come back to the original dynamics to have our alpha. And so this is why there are these conditions. Okay, so from now on, I will suppose that somehow these conditions are verified, and we will try to use it to solve our synchronization problem. Okay, so another remark. So in case in which you have linearity with respect to the input, so this is a special case of the previous more general case of input-affine. Well, in this case, since you want to satisfy the Killing vector property, you should look for a constant metric P and not for a Riemannian metric P. And in this case, you obtain this condition, which is again somehow a generalization of the Demirovich condition, but for feedback design with a linear gain. Okay. And then starting from this, of course, there are some literature also to have a more constructive design. For instance, if F is somehow a Lure system, so linear plus some sector bound nonlinearities, you can also specialize this design and came out with the LMI condition, linear matrix inequality condition, and so to have a constructive way of finding this gain. So for instance, we addressed this in this previous work. Okay, so now we come back to our synchronization problem. We want to find the distributed feedback law, and the goal is to find this phi that we will design through the sufficient set of sufficient conditions that we have just seen. So far, I will just address the problem for two cases, and I will just give a sketch of the proof, and you will understand why it is so difficult. In particular, I will consider just undirected graph in two conditions, with a leader or without leader. So if there is a leader, the leader is communicating to some agents, but then the overall communication between all the rest of the agent is always bidirectional. If there is no leader, then it's undirected, so the communication is always bidirectional. And so we have this theorem, which is suppose that you have these dynamics, suppose that the graph is undirected and connected, of course, and suppose the sufficient condition that we have seen before for the existence of a feedback with infinite gain margin, incremental global exponential stability property are satisfied. And then the global uniform exponential synchronization problem is solved with the standard distributed feedback, in which you do basically each agent compute the difference with the gain alpha from each state to the other state. Okay. And of course, you have one parameter kappa, as in the linear case, that again you have to tune just based on the connectivity of the graph. So this the Laplace, the eigenvalue with the smallest real part. Okay, so let's have a look, but very quickly, at the sketch of the proof to see how it is done, because this will show you that is not easy. It's not easy at all.
Can I ask you something?
Yes, sure.
But how does this case star depends on the connectivity? So connectivity is the second eigenvalue.
Yes, exactly. So basically, it will be 1 over lambda.
So if I know a bound on the second eigenvalue, can I?
Yes.
Sketch? Okay.
Yes. So basically, it's exactly as in the linear case. It's 1 over lambda 2, basically. So again, the main issue is that in the linear case, your synchronization problem can be seen as a simultaneous stabilizability property. But in the nonlinear case, you cannot do the same. It's much more complicated. So you cannot just do change of coordinates and say, okay, because in the linear case, when you do change of coordinates, the dynamics is the same. But in the nonlinear case, you have to consider difference between f of x minus f of y, for instance. So it's much more complicated. So this is why it's not so trivial to find a solution to the case. But ideally, if you have just one system, this condition would solve this somehow simultaneous stability property, thanks to the infinite gain margin property. So we have a conjecture, which is that this design is actually works for any graph topology. At least in simulation, this is what we see, but we have not been able to show it, but mostly because we don't have the Lyapunov function to achieve it. And so the main proof is how to find the Lyapunov function for the overall networks to certify synchronization of the network. And I will show you in just 1 second that if you have a leader or without leader, the proofs are substantially different. The Lyapunov function that we are going to construct are very different in their nature. So what is behind? So first of all, is to consider the Riemannian energy between any two agents, which is again the object that I was showing before, which is not so important at this form. In the linear case, you can think about just the quadratic Lyapunov function with the error. And then once you have this, so in the case of leader, what you will do is to take in consideration the energy between the leader and any agent in the network. Maybe this one is clear. So suppose that you have this graph. So you have a leader that share information, and all the others are exchange information among them. So basically, what we do is to consider a Lyapunov function, which is the sum of each Lyapunov function for the distance between agent, the leader, and each agent. This is the main core of the lead. And you use this Lyapunov function, you do all the derivation, and you can show that this Lyapunov function is decreasing and exponentially. In the case without leader, however, the proof is very different. And what we are going to do is to rely on the Laplacian, edge Laplacian matrices. So in the case of undirected graph, the Laplacian matrix, it can be decomposed as follows. So with the edge transpose, some weights, and then again edge, where edge is the edge matrices that define somehow, describe how the edge are interconnected via, so describe the links and not the vertices, basically. So then you take all the edge that you have in your graph, and what we are gonna do is to build a Lyapunov function that sum all the energy of the edge. So again, if we go back to this picture, what we are gonna do in this case is to consider any edge, any Lyapunov function describing the energy between the distance of any two agents that are connected with an edge, and to sum up all this Lyapunov function with the corresponding weights describing the undirected graph. So we see that the Lyapunov functions we are using are very different in their spirit, because in one case you just look at the difference from the leader to any node in the network, while here we need to consider all the difference between any two agents that are communicating. So computation were much more involved. Maybe we were just not good enough to find a common Lyapunov function for both cases. We will see. But this is why also it shows somehow that constructing a Lyapunov function for the directed graph, it's not very easy, because if in case of directed graph, you don't know exactly which kind of energy you should take into consideration.
But this Lyapunov function that you are using in this case without a leader is not working fine in the previous case. Why? Because it seems to me that in the previous case you have the Lyapunov, because in the previous case, since you have the leader, you collect information, and at the end of the story you have to synchronize with the leader.
Yeah.
Is enough to have this information. Exactly. In the other case, without the leader, it makes sense to me that you have to collect information about all the connection.
Yes.
But it seems to me that this is also working. I'm wondering if this is also working for the leader case or not.
should try to do the computation. It's a good question, but I don't have any answer. Well, thanks.
So then, sorry for the question, but again about this directed or undirected. In
Yes.
the linear case,
Yes.
the solution I missed that was for directed or undirected.
For the linear case, there is no basically difference, because if you do a proper change of coordinate, you will have independent dynamics, which are all decoupled, in which, again, for each dynamics, you need to solve a simultaneous stabilizability problem.
But you know that the eigenvalues are not necessarily real and you don't have an orthogonal.
I know. Then you have to be a little careful about what does it mean to have a linear dynamics in which you have a complex eigenvalue. But if you want all the details, they have been written very nicely in the book of Isidori recently, in 2017, and I can give you the references to handle this issue, because you're right, it's complex values, so you have to be careful about what we are talking about.
Daniele.
Yes.
I was wondering about your about the case of directed graphs, maybe at least for strongly connected graphs. You can use Lyapunov function, which will be a Lyapunov function with the where matrix will be also multiplied by the terms inverse proportional to the eigenvector.
Mm-hmm.
And then in the derivative of the Lyapunov function, if that's my guess, you will have, instead of Laplacian, you will have another matrix, but which will be symmetric, which in the end, with this additional diagonal term, you transform your non-symmetric Laplacian into symmetric.
Okay, I see. Maybe.
Laplacian, and then I guess that the same Lyapunov function, the same
Maybe
distances
works.
can be used.
Yeah, maybe. Let's talk about next time I come to Paris, Helena.
Okay.
Thank you very much.
When are you coming?
I don't know, but I need to come to pass by in February or March.
Okay, perfect.
Keep you posted. Okay. So this is just an example, because one thing that is complicated, again, there was a nonlinear PD to solve, and you may think, okay, how can I handle with this? So in these cases, we were trying to solve the synchronization problem for Lorentz oscillator, because they are chaotic and nonlinear, so it's a nice example. And to complicate ourselves the life, we put some G here that has this form, so that, okay, you are not feedback linearizable. So this was the first point. And then second point, here you have a polynomial function, because it's just polynomial. And here you have a trigonometric function. So if you want to find a solution to the nonlinear PDE, well, good luck. So of course, how to find it, I don't know. No idea. So what we did, because it's trendy, but it works well, is to try to use a deep learning approach. So to train a neural network so that it can approximate this as best as it can. And so we just trained a P, then we somehow with some trick, we discretize it to integrate the feedback alpha. I don't want to go into the details, but basically you make a grid of points, you learn the P on over the points, and if the Lipschitz constants are not are smooth enough or are small, or basically if your grid is they are dense enough, then you can hope that in between any 2 points, the metric will satisfy your condition. This is what happened. And basically then you can take like a cost, which takes into account minimizing the parameters such that your inequality is satisfied. You have the killing vector approximated, because imposing 0 you cannot it, but you can do it as best as you can with an epsilon precision that you can impose. So far, so on. And actually it works pretty well. So this is just a simulation in which we have, I don't remember how many agents, maybe more than 10, but you can actually scale up very nicely. Of course, you lose global property because you are doing some approximation of your neural network on a compact set in which you are interested. So you will not have global exponential stability, but just maybe somehow semi-global, depending on the compact set in which you trained your network. But it works pretty well, and you can still recover asymptotic synchronization. So it was pretty efficient and was really good. And the key point is that, okay, we are doing somehow neural network approach. So you don't know a priori if the algorithm will converge, but if it is converged, it will converge to a robust solution, because exponential stability is a very robust property. And so even if you perturb a little, you are still exponentially stable. So you make your optimization algorithm, if you find a solution, then it is a very good solution. And it is also robust. Here we put also some random noise, and we see that we are somehow an input to state stability property in which you have a residual that depends on the noise, but it is not making crazy stuff. So it was very nice. Okay, so this was the first part of the talk, dealing with the continuous time case. And then what we try to do is to somehow see if we can reuse all this machinery of contraction in the discrete time case to solve our problem. So in the discrete time case, however, things are a little more tricky. And here I briefly recall the linear case again, because it is instructive to see what are the limits of the solution that we are trying to solve. And there is a remark which is important, that we are considering non-normalized Laplacian matrices. I say this because in the literature of discrete time multi-agent system, most of the results that we could found deal with the normalized Laplacian matrices. And in this case, all the eigenvalues of the Laplacian are between 0 and 1, let's say. In our case, we wanted just to be a little more general and not to impose this constraint a priori. So we look at for the case in which the Laplacian is not normalized. So the eigenvalues can be anything. Well, in this case, it is not true anymore, the nice result that we have in the continuous time case. So in continuous time case, we have a nice result, which is AB stabilizable. The graph is connected, or there is a directed spanning tree connecting everything. Then you solve your synchronization problem. Well, in the discrete time case, this is not true anymore. And I will give you a very simple example in the next slide. So what you need to have, again, well, of course, you need a directed spanning tree, but then you need to find a K that solves the simultaneous stabilizability property for any lambda that is an eigenvalue of the Laplacian. And this is where there is this critical point, is the fact that in the continuous time case, we have this kind of infinite gain margin property. You have a gain that we can push as much as we want, and you can somehow compensate for any lambda that you want. But this is not anymore true in the discrete time case, because you need to go back to the unit circle. So it is not a high gain property that you can force. It's more as low gain property. And so this poses some issues. So let's see this very simple example in discrete time case. It's linear scalar. So we have A equal to 2, unstable dynamics, B equal to 1. And we consider this very simple Laplacian matrices, which has eigenvalue 0, 1, 3. And then in this case, you will solve your synchronization problem if you can find a K such that A minus lambda I bk is sure for any lambda I. And this imposes you two conditions, because we take the Laplacian, the eigenvalues lambda equal to 1 and 3, meaning that we want 2 minus k smaller than 1, and 2 minus 3k is smaller than 1. And actually, since the solution there is no compatible solution, because the first one is satisfied if k is between 1 and 3, and the second if k is between 1/3 and 1. So there is no k that can stabilize simultaneously both pair of matrices, so you cannot solve your synchronization problem. So in discrete time case, when you have a non-normalized Laplacian, there are constraints that imposes some criticism. So of course, we want to find a solution for the nonlinear case, so we need to be very careful about this. Okay, so what we can find as a definition for the discrete time case is not the definition of infinite gain margin property, but complex gain margin property, meaning that you have that this complex gain margin property if A minus lambda bk is sure for any lambda in somehow some disk which has some center C and a radius R. So lambda is not just between 1 and infinity, but is constrained on a disk. Okay. And the point, so the overall goal will be to find a case such that we have a disk gain margin property able to cope with all the eigenvalues of the Laplacian matrix. So this is really the key ingredient that we need in the discrete time case. So for instance, in the previous case, with A equal to 2 and B equal to 1, if I fix, for instance, K equal to 1.5, of course, if I do 2 minus 1.5, I get 0.5, which is a stable eigenvalue for the discrete time case. And in this case, once you fix ABK, I can compute the disk gain margin property. For this example, we have radius 2/3 and center 4/3, meaning that if your Laplacian matrices has all the eigenvalues between 2/3 and 2, because we need to do this computation, simple, then you can solve your synchronization problem. So we see with this very simple example that there are much more constraints to satisfy from both sides. So then it depends really, given a Laplacian, what is the best that I can do, or given the K, what is the kind of set of Laplacian that I can solve. It depends on which side you are looking for. And so the key point, well, how can we find a K somehow maximizing this disk gain margin property? So this is the first question. And second question will be, how can I extend this property to the nonlinear context? Okay. So one solution, I have no idea if it is optimal, actually, to be honest, but is to rely on the modified algebraic Riccati equation inequality, also called MARI in some literature. And basically what we are doing is, again, very similar to an LQR problem in discrete time context. So it's very ugly because in discrete time you have always the cross product and quadratic things. So you have APA, which is the autonomous part, and then you have all these terms that come from the gain and decay. And if you solve this inequality, so given A and B and some R, yes, I should have written given R. If you find a solution to this algebraic Riccati inequality for some sigma between 0 and 1 and for some rho between 0 and 1, so rho is somehow the decreasing rate, and sigma, since it is what goes as a factor of the control, tell you how much you are robust with respect to the variation in the feedback gain. This is the interpretation. Well, if you find this, then you have a controller K, which is defined as this, which has a complex gain margin property, and actually we characterized the center and the radius. Okay. Based on this, what we try to do for the nonlinear part is just to extend this inequality to a nonlinear setting, and in which, as before, before, what we have done is, instead of looking at A, we look at the Jacobian of F, because we look at that somehow differential property, and here we are going to do the same. So in the discrete time case, I will look for generic nonlinear time varying system. By the way, small remark, what I've shown in the continuous time case, you can generalize it to the time varying case if you find the matrix as before. Okay. So here I look at for the discrete time case with time varying case, just to produce more funny dynamics when you do simulation. I will use the notation x plus to set the next iteration of my algorithm. This is a notation which is quite common in hybrid system literature, for those of you who are used to. We denote the solution of time t with initial condition. And again, the sufficient condition that we have for incremental global exponential stability is the following one, which is the fact that, so here in the linear case, we have APA smaller than rho p, and here we have Jacobian P Jacobian smaller than rho p. So it's a very trivial, somehow direct generalization. And this condition is also known as discrete time Davidovich condition. So it's well known in literature since a lot of time. The one critical point here, I'm considering P, which is constant. So I'm looking for Euclidean metrics. There are some results to extend P of X, so nonlinear metrics P. But we will see for the design of the feedback, we have some points which are blocking and we don't have a solution yet. So this is why I will just focus on Euclidean metrics. And in this case, this condition is just sufficient, but not necessary. Okay? And so for the design, we will look for F and BU, so linear in the input. In this case, again, it is the generalization of the Mali inequality that I showed before, in which instead of A, you take the Jacobian of F. So it's really straightforward. If you can find a solution to this, then again, you have the closed loop dynamics is globally exponential, incrementally globally exponentially stable, with a feedback that has this disk margin property, because K can vary between C minus R and C plus R, here in front of the feedback. And in this case, we characterize it, so you have somehow some margin property on the feedback, which is the ingredient that we need for the synchronization problem. Yeah, this is just a remark. This nonlinear inequality, which is again ugly because we have the Jacobian times the Jacobian itself. You can reformulate it using Schur complements and some tricks as a generalized eigenvalue problems with some LMI conditions. So again, there are constructive way to simplify the problem. I will not see the details because it was too long, the presentation. Okay, and so the result that we have for the discrete time case, in this case, so we have this kind of dynamics, so we are linear in the input. And the graph here is as a direct spanning tree, but can be directed. So I don't know why, here the proof is different. I will maybe comment later on this, but in this case, we don't have any restriction on the graph, except that it has a direct spanning tree. So we suppose that the sufficient condition that I just showed for design a stabilizing feedback give you global incremental exponential stability are satisfied. Of course, you have somehow a compatibility property with the disk margin property and where the eigenvalues of the Laplacian matrices are. So somehow they need to be compatible so that you can find a feasible solution. And if you have all of this, there exists somehow a subset D, such that for any K in this subset D, your distributed synchronization feedback will solve the synchronization problem. Here is just a remark that in the proof, again, since we cannot deal with the complex number in the nonlinear case, these conditions are a little more restrictive. So if you apply this theorem to the linear case, you will find more restrictive condition because the proof is different. In this case, yes, but here I have just the example. Just a comment, why the proof, so here the proof is very different. The proof that we used is just the sum of the Lyapunov function from the leader of the direct spanning tree to any agent in the network. Now, why does this work? But basically because when you do the computation in the discrete time case, you always have like square product appearing. So all the cross products are handled in a completely different way, and we could come up with a solution for any kind of topology. While in the continuous time case, you make the differentiation, you don't have cross products in the same way, and we couldn't solve the problem for any graph. So far we don't have this kind of analogy.
Daniele,
this is just a simple example. Yes?
Just a small question. In continuous time case, if you assume that you can find constant matrix P, will it work or not?
Not sure. We tried, but we failed. Maybe we were just too bad.
No, it was just a question out of curiosity.
Yeah, you're right. But no, it was not that one, the question. One day I will show you the proof and we can discuss about it.
Okay, thanks.
Thank you, Elena. And so in this example, we just consider somehow some nonlinear function f, which are sine, exponential kind of things. To solve our nonlinear algebraic equation, modify the algebraic equation, we use somehow a polytopic approach. Basically, you look at the worst case for all the function, and you hope that it works everywhere. So we could find a feasible solution for it. Will not give all the details. And again, the solution was nice. So these are the open loop state trajectories with the noise. So I think the system are unstable if you just have the open loop dynamics. And when you close the dynamics, you can see that you are stabilizing to an unstable solution, but it's not an issue because this is the feature of synchronization problem itself. And we see that again, the solution is very nice without noise and robust when there are noise. Actually, you can show that also you have some incremental stability property, not only global exponential stability. So let's go to the conclusion. So the recap of all this result, in continuous time case, we look at the input-affine nonlinear dynamics with undirected connected graph topology, with Riemannian metric condition to obtain contraction or incremental global exponential stability, and some design condition can be relaxed using Euclidean metrics, approximation, LMI. So I've not shown all of these, but if you're interested, I can point you to some results existing in the literature. We also have, I've not shown it, but some guarantees that the relaxed condition, for instance, is scaling vector field property, etc., does not destroy your synchronization problem, although you are not anymore global. In the discrete, so the open point, again, is to extend the theory to any graph topology. So this is the key point that we have not looked at. In the discrete time case, however, we have looked just at this kind of dynamics, which are linear in the input with the Euclidean metric, but any graph topology. And so the open point is to how to extend the theory to general input-affine nonlinear system. One of the blocking point here is that the theory that I showed before in the continuous time case with these killing vector field properties and the nonlinear PDEs has not been developed yet in the discrete time case. So it works nicely for the Euclidean case in P constant, but when you have P, which depends on the X, is a mess. And why so? Because when you do the next iteration, you will have the P depends on F and G as the arguments. And these create a mess in all the computation, and we don't have a good structure yet. So this is the blocking point, basically. So I've not shown, but we have also combined somehow the continuous time and the discrete time case to handle hybrid system under the condition that all the jumps are synchronized. And this is just the references of this talk. And thank you very much for listening.